Good afternoon, everybody. Welcome to our August webinar on engineering timber for better performance and efficiency in construction. I see there's still a few people coming in the doors, so I'll just do some housekeeping as those people come in. We'll have three very insightful presenters today. Franco Piva, who's a director at Ergodomus, and he'll be talking about from mass timber to smart timber, avoiding mess timber. We have Michael Kloos, who's a structural engineer, and he'll be talking around tips and tricks for timber design and detailing. And Dr. Dan Tingley, who is the Global Senior Structural Engineer and Wood Technologist, and his presentation will be on advanced fiber solutions for timber performance and durability in the marketplace. We have 201 registered attendees today, which is great. I see only 81 or 82 have joined us so far, but hopefully that will tick up as we move through. Just on the CPD points, as we mentioned in the invitation email, there have been some internal changes at the South African Institute of Architects, so we were not able to obtain CPD accreditation as we've done for previous webinars, and so we are still engaging with other architectural bodies, and we hope that you'll just be patient with us in that regard. But today's webinar is accredited by the Engineering Council of South Africa as a Category 1 CPD activity for 0.3 points. However, to qualify for those CPD points, you have to attend this webinar as well as our webinar on the 6th of November. So hopefully you can just save the date in your diaries, and we will be sending out the registration link in due course. So apologies for that and any disappointment and inconvenience that might cause. And we're also grateful for the support from Sawmilling South Africa, from the University of Pretoria and the York Timbers Chair, the Stellenbosch University and the Wood App team, as well as the Department of Trade, Industry and Competition and Earthworld Architects. I call them the brain team, and they help us to select the topics, engage the speakers, so always thankful for that. And of course my wingman Ferdinand Hassan is always grateful for his back-end support. So I'm going to let me talk through a few announcements and some dates to diarize over the next month. So Ferdinand, you wouldn't mind just skipping to the next slide. There we go. So of importance is the Growing Timber Connections Conference, which is in September. There's the colloquium on the 8th of September and the actual conference on the 9th of September. I was there last year. I'm not an architect. I'm not a structural engineer, but it was fascinating to see the work that is happening in the timber and wood construction and wood engineering space. So it's a not to be missed, and it would be well worth the trip to Johannesburg or Pretoria if you can make it. So there is the website there to get more information. And then we also have the Wood App workshops also taking place in Pretoria at the same venue. So they'll be running concurrently. So you're going to have to, maybe divide and conquer if you've got a colleague to see who can attend the workshops and who can attend the conference. I'm going to hand over to Roy Southey. He's the executive director of Sawmilling South Africa, just to give us a few opening remarks. Over to you, Roy.
Thank you, Sam, and I think you've done such a good job of welcoming everybody that there's nothing left for me to do. However, we'd just like to say on behalf of Sawmilling South Africa and the rest of our sponsors here today, welcome to you all. It's very encouraging to see that there's so many people in the audience. I hope that the bulk of you are either engineers or architects, the kind of people that we target with these workshops, webinars, in an effort to spread the word of the virtues of building with timber. And then, of course, to our presenters today, Franco, Michael, Dan, and of course not forgetting Tafadzwa from the DTIC. Thank you to you guys, and we certainly hope that you're going to impart some wisdom to all the guys that have tuned in today. I realize that many of you, as I say, will be engineers, and we know, of course, that engineers know everything in the world. But we're hoping that our experts will impart a little bit of enthusiasm into you guys, and we hope you enjoy it. We certainly hope that it adds fuel to the fire, and that this whole the whole movement towards a greener future, a more ecological friendly building method picks up pace, and we all see you guys using more and more timber. It will, of course, be really beneficial to my members, who are all sawmillers who produce the material that you require. And without anything further ado, we'll hand over to you, Sam. Thanks very much, and enjoy the webinar.
Thank you so much, Roy. We'll keep things swift because we do have 3 presenters today. I am going to hand over to Michael Kloos, and as I mentioned, he's going to cover tips and tricks for timber design and detailing. So over to you, Michael. Thank you so much.
My name is Michael. So this is the short presentation overview. I'm first going to give you an intro into who I am, and then I'm just going to jump straight into the tips and tricks. So the focus is on CLT and mass timber, but really a lot of them are sort of applicable to timber in general. And some of these might be quite elementary or basic to many of you if you have experience with timber, but some of them I hope are something new. Many of these things I sort of had to figure out myself when I was new to timber, and I wish someone had told me this when I was starting. So I'm a professional engineer. I'm registered with EXA. I've been working for 7 years, worked with all kinds of materials, but I really love timber, and I focus most of my attention on timber, and I'm based in Cape Town. Firstly, the very high variance of timber. So conventional materials that we work with are man-made and have, you know, fewer very highly defined mechanical properties that we know very well. So concrete has 2, steel has 2, brick only has 1 really. But timber has 7 strength values that we use. And this can sort of be a bit overwhelming when one starts, because, you know, what do you do with all these values? But I think to understand why it has these differences, I think is an important thing to understand. Would you rather have to gain a fundamental understanding of where wood comes from, then you understand why it has all these different values. So basically, wood has not been created by humans. It evolved in nature to serve a purpose within a tree, and it's done that exceptionally well. If you look at the tallest trees, they're 116 meters tall. That's, yeah, a 10-story building is 30 meters. That's just sort of put. So let's look at a tree and see how it grows. So as a tree goes up, the compression at the bottom increases because of the weight, and then as the wind comes from the side, it bends it. So it's natural that these 2 properties, sort of bending and compression parallel to grain, are by far the strongest. But then if you look at how timber grows, it grows lots, you can think of it as lots of little straws bound together by elastics called lignin. And it has very little strength from the sides, which is natural, because why would a tree need to be strong in that direction? So to give a comparison, the weakest property, which is tension perpendicular to grain, is 1/50th of the strongest property, which is compression parallel to grain. Keep in mind, this is just S5 structural pine in South Africa, but in general, the ratios within timber are similar. So that just gives you a bit of a background why the properties are like this, and that just helps to sort of wrap your head around the material. All right, the next is the serviceability design. So timber has a very high strength to weight ratio. It's higher, in fact, than concrete and steel. So this is great, but it comes with the downsides that the lightness and flexibility leads to other problems, namely deflections, vibrations, acoustics, which is sort of together called serviceability. So to actually break a piece of timber, you have to work extremely hard. So at this picture, you can see we're bending a piece of CLT rig, and it basically, you have to put it into a banana shape before it actually breaks. So long before this happens in a building, people will look or feel unsafe in the building, or uncomfortable, or it's going to sound really terrible. So, and then here's just a little test piece of how amazing trees are and how flexible they are. This is close to where I live, and this is where the wind has pushed this tree over many years, and it's actually grown into this shape. Huge cantilever, incredible flexibility, and it's still standing there. So what is the solution for serviceability? Similar to other materials, you use your typical deflection ratios, like span over 300. But important with timber, similar to concrete in some ways, is you have creep. You have to allow for long-term deflection, and this is quite high. It's more or less 1.6 for SA pine in dry conditions, but if it's wet, it will go up a lot. If you have loads that are, if you have more long-term loads, it can go up as well. So just because it meets the deflection ratio in the beginning doesn't mean you're not going to have problems down the line. For vibrations and acoustics, I'm not going to go into detail, but for vibrations, I suggest going to the Eurocode, and for acoustics, basic strategies are changes in density, separation layers, which break up the sound waves, and this would be like rubber pads between timber elements, or double wall, something like that. But yeah, I recommend that you consult with an acoustic designer or suppliers for help. So my warning or my advice here would just be, don't proceed too far down with ULS design, strength design, without considering these things early on. For serviceability, a nice starting point are the span tables. So these quickly give you an idea of what it can, what it can and can't do. However, you need to understand the limitations of span tables. All of them have got assumptions that have been made, and you need to match those assumptions to your structure. If your structure has different loads or deflection limitations, you need to take that into account. So it's really only a preliminary tool. Where to find these? So for CLT, the manufacturers, they have their own span tables. And for regular timber, you can use SANS 1.2, which has span tables for your typical joists and rafters for residential and commercial construction. Next tip or trick is the pre-planning of services. I think if in the planning stage, it's highly beneficial to think quite carefully what those services are going to run, namely electrical and plumbing mostly. For timber framing, it's arguably a bit simpler because you can run it in the wall. There's voids in the wall. Through the studs, ideally through the center line. However, when it comes to the waste pipes, the 110 waste pipes, you have to think a bit more carefully because the typical stud is only 110. So you need to consider where that pipe's going to go. Otherwise, you're going to lose your entire stud. For CLT walls, it's a little bit more complicated because we don't have voids. It's a solid piece of timber. So for electrical and for chasing, you can only go vertical on your walls. You can't really go sideways because it weakens the wall too much. If you have an external wall, you can run it quite easily on the outside of the building, but you have to take into account how much space you have. And for timber framing, what you can also do is you can use timber framing walls on the inside in certain areas to create voids where you can then run your services. So for instance, what we've done before is had timber frame walls by kitchens and bathrooms so that we can run our services in there. So here's just an example of a waste pipe where we ran it on the outside of the building. This is a plan view of a CLT wall, but we still had to then recess a 55-inch deep groove so that we didn't build up the cladding too much. And then this is something, again, if this had not been planned before, you would have had to have cut this groove on site, and now you're compromising your treatment, and it's just difficult to make these kind of cuts on site. So this requires looking and thinking about this early on. Here's an example of electrical chase. Again, these are pre-cut grooves for your conduits. And then we made it wide on the outside for a cover strip. And the reason for the wider strip was just for visual reasons. We didn't want to have such a thin cover strip. All right, next tip is the screws. So there's a lot of different types of screws out there, but I think the most important difference to understand is partially versus fully threaded screws and why use. So the first one is the partial thread screw. This is quite familiar to most people. There's a smooth shank and then there's a thread. These screws are great to pull and clamp pieces of wood together and close gaps. So it's very useful during the initial construction phases when you're trying to just put everything flush and straight. There's a lot of different head types, and these head types fundamentally govern the pull-out capacity because it's the head that actually gets pulled through the timber when it really goes under load. So the type of head you specify will have a big influence. For instance, you get these mushroom head screws with much wider heads, and they work a bit better if you're needing that axial capacity. And then we get our full thread screws. So these are more specific to structural timber. They are incredibly strong because you're engaging the wood along the full length of the shaft. You're getting bearing everywhere on the thread. You're not just bearing on the head of the screw. They are more difficult to install though. They provide more resistance and they are more expensive. However, the way it fully, let's say, activates the timber and holds it together is great in a structural or in a building because you really want to hold that building together. So a common construction methodology for CLT would be to use your partial thread screws initially during assembly. And then once the building is up and everything is flush and you're happy, then the structural fixing comes with the full thread screws. Because if you install one of these screws and there's still a gap between the two pieces of wood, you will never be able to close that gap later because the screw will hold them in place. Okay, the next one is pre-drilling and whether or not to pre-drill. So the short answer is that ideally you'd always pre-drill because it has several advantages. It reduces the chance of splitting wood, especially if close to the end. And perhaps counterintuitively, but the connection is actually stronger. Why? Because as the screw goes in, it pushes the timber away and causes little tears and cracks and reduces thread engagement. If you pre-drill, your thread cuts nicely into the timber and you get full bearing capacity with the thread. However, the reality is that pre-drilling takes a lot of time and it's a nuisance on site. And the modern screws these days are quite effective at self-tapping. So yeah, ideally we'd always pre-drill, but I think in reality, I only really specify pre-drilling if we're going into hardwoods or if you start using really, really big screws. Right, end grain. So this is an important one. If you put a screw into the end grain, it's very weak. So you're only going to get about 25% of the cross or side grain capacity. So whenever you're going into an end grain, it's much better to just try and go at an angle. Eurocode specifies a minimum of 30 degrees. This will just enhance the pull-out capacity. Okay, some general tips for connections is to keep it simple. Use less types of screws on site. Don't specify 10 different types of screws if you can specify 3 or 4 different types of screws. Keep your details repetitive and consistent. I think especially within the South African context, if you were in something like CLT where you might be working with contractors who aren't familiar with the methods or the material. And then to keep complex connections for complex buildings and simple connections for simple buildings. Consider your fire resistance early on in the design process if you are needing to do a fire design. Connections are critical in the fire system. And then a useful rule of thumb for timber connections is that a large number of small diameter screws or dowels or nails perform better than a small number of larger diameter fasteners. So it's better to use lots of small connections as opposed to fewer big ones. Of course, this does take more time on site, so there's a balance, but it's just a fundamental sort of rule of thumb for timber. All right, the final tip I would give is that don't underestimate waterproofing. Water is magic. It can go in any direction and it will find its way into your building if you're not careful. So in my opinion, you always need to have at least 2 lines of defense against water. You cannot rely on only one system. There's too many variables at play, human error, material. So it's in your favor to be safe here, even though it's going to be a bigger cost. You're going to save yourself a headache, and you're going to save your client a headache if there's ever a problem. The added risk here is that water is not just a nuisance in a brick building or concrete building. If things get wet, it's obviously terrible. There might be mold or paint coming off, or it's leaking, but it's not a structural threat in the sense that it's not damaging your material. Whereas with timber rots when it gets wet and stays wet, and that weakens the material. And in the worst case scenario, if you don't know it's leaking and it's in an area where you can't see the timber could be decaying and it could eventually fail. So there's an added level of risk when it comes to water and timber buildings. That means you really have to prioritize waterproofing in your design. Thank you.
Thank you so much, Michael. I see there's a question here from Newton Hill. Will you be covering protecting timber from rot and damage from insects? Yeah, I don't know if that's something you can answer to, or perhaps one of our other speakers can speak to.
So what's the question?
How do you, protecting timber from rot and damage from insects, pests?
Well, to protect from rot, basically, it's quite simple. You just keep the timber dry, or actually, more importantly, you let the timber breathe. So timber doesn't mind too much getting wet. It doesn't like staying wet and humid. So to protect from rot, that's the only way. You just make sure your detailing keeps it dry, and if it gets wet, allows it to breathe. And there's specific products for that. In terms of insects, you treat it. You treat CCA treated or Glybor or whatever. There's the products that you use chemicals basically that you use to treat your timber.
Okay. Thank you. Newton, I think you can also contact the South African Wood Preservers Association. They can also guide you in that respect. Roy, I saw your hand up. Was that something you're going to add?
Yeah, just you covered that, Sam. South African Wood Preservers will push you in the right direction and give you all the advice you require. Timber is pre-treated, and most of the timber that is specified in the building codes in South Africa requires pre-treated timber, which takes care of rot and insect damage and what have you. And if you go back in the webinars of the past, you'll see that we covered this subject quite comprehensively a couple of months or a year or two ago, and you'll find it obviously on the website. So there you go.
Thanks, Roy. Yeah, Ken, if we can, we're going to move on, and then if you could just keep your question to later or put it in the chat, please. I'm now going to hand over to Franco Piva. He is, again, going to talk from mass timber to smart timber, avoiding mess timber. And Franco is joining us from Toronto. So he's a very early morning for him in Canada. So yeah, welcome, and over to you, Franco.
Thank you, Samantha. Yeah, it is 7:30 a.m., so it's not that bad. But yeah, still early morning. But I'm originally I'm based in Italy. I'm here for business just for a few days, and I must say that I was laughing when Michael before me said water is magic. Is more than magic. Is incredible what water can do, and how much it can destroy timber. It can make timber rotting. So durability is something I've been working on for years. I love timber. I've been designing timber for more than 20 years so far, but durability is always there. My first priority is always durability. So thank you, Michael, for raising this question, this problem. So if you haven't used timber for your projects, don't worry. They told me, I found this on Google. That is an African proverb. The best time to plant a tree was 20 years ago, but the second best time is now. So I'm happy that Samantha and the other guys and the sponsors organized this webinar to show people what you can do with timber, how to use it. I was a couple of years ago in Pretoria at a conference, and I really suggest you to go there to see how the market is evolving. It's a great event. I really enjoyed it. I'm Franco, and I'm the director of an engineering firm called Ergodomus Timber Engineering. We are based in Italy, in the northeast, in the Alps. So it is an area where it is quite common to use timber for the structures. And in this slide, I collected some projects we worked on in the past years, and basically in the past 18 years, more or less. There are projects from many different countries, I would say from all over the world, basically mainly in Europe, but we also have some projects Canada, US, North America in general, South America. We are completing a project in South Africa at the moment, taking care only of all the engineering aspects. Worked quite a lot in Australia and Singapore, because we started from Italy, but then we saw that the market was growing very fast. There were new players interested in using timber, new way to use mass timber, especially I would say North America. For a few years, the market was really interesting. It is still interesting. A lot of things are changing, especially because of the tariffs. I'm also here to better understand what is happening between those two countries. But in any case, it is something very, very interesting. I'm asking you something. This is a question. There will be also another slide with the same question in a while, because I would like you to think about what could be the number instead of having XX. What could be that number? What is the percentage of construction time, site time, unproductive? I mean, if we consider 100 days the construction time of a building, how much do you think the unproductive time is? I mean, 20 days, 30 days, 50 days, 5 days. I'm not talking about the productivity, I'm talking about unproductivity. So if you say 10%, it means that considering 100 days, it will be only 10 days people are unproductive because they are waiting for material, because they do not have the right information, because they have to rework on something. Just think about this number. And don't use Google, please. Try to think it is in a few minutes. I will tell you the last slide will be the solution. But try to think what could be this number, 10, 20, 50, 40, 90, whatever. Try to think about this during my presentation. What I can say for sure now is that mass timber helped us to change the market a lot. It brought a revolution to the market, because finally we are really talking about the digitization of all the processes. We can really use tools like BIM, Building Information Modeling. BIM is a 3D model. It's not just a 3D model. It's more a 3D model that can speak, that can give us a lot of information, give us information about the geometry, about the name of the elements, about the maintenance of the element. You can read everything just using a shared 3D model in a standard format, which is IFC. And we can also, for sure, use robots to prefabricate the elements. I'm not talking about science fiction, I'm not talking about rocket science. I'm more talking about what you can do once you realize that the material you're using is a digital material. We see timber on site, but before having a CLT panel, before having a glulam beam on site, there is a process to engineer it, to draw, to prepare the 3D drawings, to prepare the files ready for the CNC machine. And the acronym I really like, which is behind the process, which is behind a glulam beam, behind a CLT panel on site. Everything is around DFMA, design for manufacturing and assembly. 3 words: design, engineering process, to draw the element, to think about how the element will be, manufacturing, how to produce it, assembly. There is something in between manufacturing and assembly, which is transportation, logistic. In many cases, we have to face, for our projects, we have to face the problem, how can we transport the elements from the factory to the site? Everyone loves prefabrication. We all would like to have prefabricated element and we assemble them in a blink of an eye on site. But how can we transport them from the factory to the site? In the factory, you can manage big elements, super wide elements. But what happens when you have to transport them? So DFMA covers all of this, from the design to the assembly, everything in between. But to have a DFMA mind, you need to have also a very holistic approach. So it means that you need to think about how the building is, not only focusing on the acoustic, not only focusing on the structural aspect, not only building physics, not only logistic. You have to have this holistic approach, and I like to use this sequence of slides showing how you need to raise your point of view. You start from 1 meter here on the top left. At 6 meters, you realize that there is something around the slab. 10 meters, you see some walls. Then 15, 25, 35 meters. If you look at just at your feet, you cannot understand how the building is. You cannot understand and solve the problems. So you really need to raise your point of view and have a global view of the project, which includes durability, structural analysis, includes building physics. Everything must be considered to design a good building. And let me show these. I'm getting closer to why Samantha said that I'm going to talk about smart, mass, mesh, timber. Why? This is a very good question. Look at the 3D printers. If you don't really know what mass timber is, it is normal, no problem. You probably know what a 3D printer is. Maybe you have already used the 3D printer to prepare a prototype, to create something you like. Look at the octopus here at the center. You see, it's a great structure, quite funny. I just Googled for it a few months ago to find some funny pictures for the 3D printers. But what I would like to highlight in this picture, do you think what was the most complicated part to have this before having this octopus in your hands? Is it the design or the production? I mean, what's the most complicated part to design it, to create a 3D model of the octopus, or to produce it? The most complicated part is the design. Once you have the 3D model and you can use Rhino or another software you like, there are many products on the market. You use it takes a lot of time to create this model, to come up with the idea, to draw all the tentacles, to draw the eyes. You have to create a 3D model. Once the 3D model is ready, and maybe you made some prototypes, then you just click 2 buttons and you can have 10, 100, 200, 500 sculptures in your hand, 300 models in your hand, no problem. But it is always the design. So the tools we have now, and the reason I'm talking about timber as a digital material, is that we can spend a lot of time in the design, but then once the design is ready, on site, it will be everything much easier. But we first need to focus on the design. So again, I said we design good, and then site will be easier. Try to think about this number or this range of numbers. I'm not giving you the solution. It is 10.25%. It will be a range between 2 values. Try to think about these numbers. In the timber industry, we are not using 3D printer, but we are using CNC machines, which means that there will be a machine starting from a bigger element, removing what is not needed. And basically what we see on our side, at the very end of our work, after we completed the production drawings, we can see on a simulator, we can see how the machine will work. We can exactly foresee how many minutes, how many seconds the machine will take to prepare the element. And we can also, of course, check if there are mistakes, if there are problems, if there are clashes in the machine. We can check everything here. We can see if the sequence is okay. If there is something wrong, here is the right time. And to check here, the model is for free. It doesn't cost anything. It's just a few minutes for us to check if everything is okay. Having a problem in the production takes a lot of time, a lot of money, a lot of problem, people yelling at you, etc., etc. So again, first design and then the production. There is a book I really like, and I suggest you to read if you have the possibility. It's written by a Danish professor, Bent Friedbjerg. In this book, the title of the book is How Big Things Get Done. And if I had to summarize the book in just a few words, 4 words I would say is think slow, act fast. Take the time to design. Timber is beautiful, but it is not, using timber is not like we start doing something and then we will see on site later what to do. No, with timber, you need to shift everything at the beginning. Design, and then you assemble the elements on site. The bad side of that is this, Pareto's principle. Pareto is an Italian economist, an Italian engineer. He lived like 150, 140 years ago. He said that 20% of the people in the world owns 80% of the money of the richest. Probably now it's more like 199, but at that time it was like 2080. I try to reuse this principle, to adapt this principle to the building industry. They use this 80-20 for many aspects, but I said, what if we try to use in the building industry? Try to think about your projects. If you're an architect, an engineer, or whoever you are in the building industry, with 20% of your time, you can easily get 80% of the results. This means that you can be very quickly at a good level of the design. But once you need to complete the remaining 20% of the project, then you need 80% of the time. It's not linear. It's absolutely different than linear. How many times it happened to you that you think, okay, the project is almost ready. I really need a few details. I print the drawings, I'm okay. So you think in a couple of days, everything will be done. But it is not, because you're here, you completed 80% of the result. Or you're happy, you say, wow, the project went very well. Just a few more details, just a few more drawings, and we'll be ready. And then it takes forever to get to the conclusion. With timber, this is the biggest problem, in my opinion, because the drawings has to be so detailed on the production side. It's not just, we are not saying that the architects, engineers need to prepare such a super detailed drawing. But as timber engineers, we need strong and reliable input from you, good drawings, because the digital model is super detailed. Every single element has to be drawn. And then once you're on site, you see that what you see on your screen, it is what you get, what you see on site. It's like a 3D printer. You create a very sophisticated drawing, but then there is a CNC machine making it, and you see how it will look like. But you have to consider every single millimeter. If the tolerances are 1 millimeter there, 2 millimeters there, 5 millimeters there, you have to draw, not you as an architect or engineer, but the timber engineers have to keep into account all these tolerances to avoid problems on site. We always aim to reduce the waste time on site. We always aim to reduce the unproductive time on site. I like Lego. I've been playing with them since I was a child. And think about this. This is one of the nicest boxes they created. How long will it take to assemble this box or other boxes? And compare this time to the time Lego took to engineer it. They took years, 1.5, 2 years, many people working on that project. But then you don't take 3 years, 2 years to build it. In a few hours, you can build this amazing car. Why? Because there is a good project behind. There is a project, instruction, you assemble it. You don't have to drill holes to change the element, to wait to have the right bricks. And again, the core is think slow, but act fast. Take your time to design and save time, a lot of time on site. So let's come to the conclusion of the last few slides, 2-3 slides of my presentation. You look at the McLemis curve is a curve telling you that this is the time, horizontal, this is the design cost, effort. And look at the brown, the orange line, the cost of the design changes. The more you go to the right, the more the changes, the more expensive will be the changes. But at the same time, look at the blue line. At the beginning, you can change completely the project. Day one, you can change everything. Low cost, high impact. Low cost, brown, high impact, blue. After a few days, it will be mid cost, mid impact. And then there is a day too late. This happens when, like after 3 months, you're working on the project, they tell you, the client or whoever, the developer, the builder, tell you, you know what, I would like you to make the building a bit bigger. That is the day too late, which means low impact, high cost. If you transfer this to the world of timber, I like to use this metaphor. Day N to day too late is mass timber. But if we start thinking about using timber on our project since day one, then it is smart timber. After day too late, and it happens many times, they involve us, or they try to involve us after day too late, it is a mess timber. And in terms of costs, this is what happens. Mass timber is quite expensive. Mass timber is terrible. It's too expensive. So the conclusion in many cases is, you know what? We wanted to go for mass timber. We love timber, we love sustainability, etc. But timber is too expensive. We better go for concrete. It can be that timber is expensive. I'm not saying the opposite. But when did you start thinking about timber? Because if you started on day too late, for sure mass timber is too expensive. No way, it's too expensive. If you started on day N, quite expensive. But if you start from day one, and as Michael said, you consider all the things about the vibration, deflection, screws, since day one, the very first day, you're still working together, architects, timber engineers, structural engineers, to come up with the most optimized solution to use timber. In some cases, it could be like you move by 30 centimeters a wall. You optimize a bit the shape. We're not talking about building boxes. We're talking about making timber the most cost-effective material to go for. But this has to be done on day one. On day too late, it will never succeed. It will be just pain and a lot of emails, etc., between the different players. So we really need to move from mass timber to smart timber. And this is the solution of the answer to the question. As a final slide, 40 to 50% of construction site time is unproductive. Try to think about the example of the 100 days. You have people working 100 days on a site. Every day, instead of working 8 hours, it's like they work 4 hours, more or less, 4 or 5 hours. Maybe one day they work 8 hours, but the day after it could be just a couple of hours. This is a general number, is based on our research I found on the internet about the productivity in Europe. Maybe in North America is a bit different, in other areas it could be a bit different, but it is always around 40, 50, 45, 55. That is the range. The most productive, the most efficient industry, or one of the most efficient industry, is the car industry, is the automotive industry, and their unproductivity is around 3 to 6, 7%. So I'm not saying that if we go for mass timber, for smart timber, the productivity will be 100%. I'm not saying that. I know it is impossible. But try to think what could be the big change if we move from 50% of unproductivity to 30%. Maybe even better, but let's consider 30%. We could reduce the cost, we could reduce the inefficiency, and we could improve our projects. So I hope that these webinars and other events like the one I hope you're going to attend in Pretoria, I hope that this will help us, help our industry to move from this 50% to something smaller, so that the unproductivity will be hopefully less than 30%. And yeah, I hope you will start to use timber very soon on your project now.
Thank you, Franco. I'm going to move on to Dan's presentation, and then we'll move to questions a bit later. So we have another person from Canada. That's Dr. Dan Tingley. He is speaking on the advanced fiber solutions for timber performance and durability. He is joining us from New Brunswick, which is on the eastern coast of Canada. And so I'm going to hand over to Dan. Thank you so much.
Well, good afternoon, ladies and gentlemen. My name is Dan Tingley, and I'm the Senior Global Structural Engineer for Timber and Wood Technology for WRD, and we have offices in Canada and the United States, Saudi Arabia, South Africa, small office with Paul Maslus there in Cape Town, Fishhook. And so our whole focus is on timber in our group, and today I'm going to talk about that. Samantha mentioned I'm currently in Eastern Canada on the East Coast, out about 1,000 miles east of Franco, on the Fundy Coast. And you can see here a little map of Canada, and then a couple of circles right where I'm located today, just for those that are interested. If you're ever out this way, come and visit. And I grew up in a province where we're notable for having the longest covered bridge in the world. That went through all seasons, 130 years old to date, working still today. And the Eastern European settlers realized that if they put a cover over their howe trusses, that would cause the timber to last a lot longer, because they kept moisture away from the joints. And we know that wood, when we get its moisture content over 24, its oxygen above 21%, and its temperature in 5 to 35, 40 degrees Celsius, is going to decay unless it's protected. So what we do with roofs is we just keep the water off the joints, and if you take the water away, wood just doesn't decay. So at WRD, we're an IES accredited test lab and third-party lab with a strong commercial engineering wing, and we write books, for example, like this, Wood Construction Systems for Australia and Southeast Asia, talking about mass timber. Who would have thought 50 years ago when I started my career that we'd be telling and teaching engineers how to build dome roofs on top of a 20-story building and put a swimming pool at the 18th floor. But that's where we're at today. And the sorts of things we do at our lab is look at fire testing to develop strategies for fire resistance ratings, assemblies of systems that will provide for fire protection, and those different fire protected systems allow us, for example, to build these high rises either using CLT or an assortment of different timber strategies. With fire test setups, either single member or assembly setups like this one, you eat at 21 test, bring her up to 1500 degrees C in 5 minutes and watch it burn, and develop an FRR, fire resistance rating, in minutes for single or assembly sections or for reinforced sections. And that's what we're going to be talking about today, is how high strength fiber has changed the world of mass timber and timber design. Using these high strength systems allow us to improve products or timber's performance in a whole host of ways. We also do these, write books, for example. This is the most recent one for the Canadian government on timber bridge inspection, maintenance, restoration, and design. Timber bridges are coming back in a big way. In 1962 in North America, 80% of our bridges were timber. By the time we reached Y2K, only less than 1% were being built in timber. Today, that's moving back to timber as cost advantage, carbon concepts are all impacting the way we think about timber in outdoor and timber structures. So these are important aspects of what we do today in our terms of our designs. Not bragging, just a little bit of expression and novelty here. In '96, we won the Charles Panko Award for Innovation for High Strength Fiber Solutions. In '97, the Nova Award, which is all construction products for high strength fiber solutions in their design. That's led to many different designs for award-winning designs. As you can see here, this bridge, which we recently won 4 different awards from Carbon. This bridge built in steel, which timber was opened in the tender. A specification allowed us to submit a timber solution, and the steel solution in this bridge was 2,760 metric tons plus. This timber solution was minus 970 metric tons. And so these are some of the reasons, along with cost. This cost was 32% less than the steel option. It took 1/2 the time, as Franco talked about, building a Lego kit, treating it after you've machined it so that there's no bright, and then building it on site in half or a third the time is the tip to winning not only these awards, but the hearts of your buyers. So 50 years ago, my designs looked like this. This is, I won an award for this one, Hector Heritage Quay, in a place called Pictou, Nova Scotia. And it represented the first time the Scottish people had landed 400 years ago in Nova Scotia. And that's what these buildings used to be in my early days of design in the 70s and 80s. This was mass timber to us. These posted beam structures with wooden dowels. Or this guy in 1988, 535-foot clear span, 14 stories high, all timber. I didn't call it mass timber back in 1988. I just said it's a glulam building. It's 2/5 of a basketball, and we're going to store coal in it because an SO2 isn't a problem for timber, and concrete and steel just wouldn't cut it. And so these structures were very popular in the day for things like potash, for example, and still are today. Flagstaff, Arizona, for example, with a Barracks dome, it's 2/5 of a basketball. Tacoma, in Seattle, Washington, as you can see inside here, all timber. And these are dating back to my early days in the 80s and 90s. This is in Vienna. It's a wastewater treatment facility. Only the Viennese with oil money could make a wastewater treatment facility look like these reinforced S-curve glulam beams. Or this one here, it's a furniture display hall. This is what it looked like when it was finished 25 years ago. And as you can see here, even a mass timber tunnel, walking tunnel in this particular building. This is under construction. And this is a unique building with a knife plate, dowel, a rigid C shape on top of a pinned connection in a concrete column. But you'll notice something even more unique than that in the left-hand picture, and that's lots of holes going through these beams, which the high-strength fiber, which is at the bottom face, allowed to happen. And of course, this is kind of the look today. And I went back to visit it last week in Vienna. I was visiting a bunch of old structures I designed back 25 and 30 years ago. And this is one of the owners here of this current building right now, very happy with this mass timber building 25 years ago, built with timber. So I have a few patents in this area, most of them off now, 42 to be exact, in this whole area of producing reinforcement using Kevlar, carbon, glass, pre-tensioning, pultrusion, pulforming, allowing the fibers to get saturated with a resin in its liquid form, kicked over in a heated die that allows it to turn into a solid, with up to 1 kilometer of fiber on one reel, 5 times the strength of steel at 1/5 the dead weight, and you produce it in all forms, and you put it in strategic locations so that the beam on the right, made out of low-grade wood, is equal in strength to the beam on the left. And that's where the advantage comes to. And that advantage comes to mass timber too. As you can see, CLT and GLB, glulam beams, 2 examples of mass timber here. Lighter weight compared to steel and concrete, fast install, reduced transport. You can prefabricate your components, environmental advantages like low carbon footprints and renewable material. Everything from nail laminated timber to GLB to solid sawn to CLT panels that go on top of these post and beam or platform frame structures. You can see LVL, another form of it, Paralam, PSL, LSL, all of these different types of mass timber, from orientated strand board to the traditional plywood. Wood is back in action. When I graduated back in the early 70s, I was 1 out of 14 people in a class. And I watched the great era of precast concrete take place in the 80s, 90s. We're 36 glulam beam plants in Canada with the highest production of glulam in the world per population, turned away to 3 plants by the Y2K. That's back on the move now as we see glulam beam plants setting up all over Canada and all over North America, producing these sorts of structures, as you can see here, in different parts of Canada. All mass timber, all going higher and higher and higher. We have an office in Saudi Arabia where they tell us now that the Saudis are looking to build a 126-story building by 2030, platform frame concrete core using CLT. So these are the ways things are going in our world today as we look at timber coming back in vogue for uses not only for swimming pools, where they're obviously a better choice due to the fact that wood just doesn't rust, as you can see here, but for a host of other reasons. These are the current structures that we see all over that are going forward. So how does advanced fiber fit into the equation here? In everything from tension reinforcements to shear reinforcements and so on. Well, The primary places that we look to have high strength fiber is used to increase the capacity of timber structures. Timber is anisotropic. That means it has different properties in different directions. And some of its weakest properties are tension perp, as we heard earlier. And as a result of that, what we can do with high strength fiber is use it strategically, like Rio in concrete, to supplant the weakness in the anisotropic material wood. But if we're going to do that, we have to also be careful that the wood is hygroscopic. That means it breathes in and out moisture, and when it does, it shrinks and expands. And so anything we're going to attach to it that is not organic and doesn't have those characteristics, we have to be very careful how we design it so that when it attaches to wood, it doesn't spall off or delaminate over a period of time. So the plane sections no longer remain plain, and it's not a true composite. So this is how we work toward this in our reinforced concepts to be able to get where we're going in terms of using high strength fiber. One of the key places that CLT is benefiting from high strength fiber is through the improvement of minor axis horizontal shear capacities in either a platform frame or a post and beam frame, as you can see here. Particularly in the platform frame, we see this problem as a big one traditionally with CLT because of minor axis, what we call rolling shear or transverse shear. And so this is a big feature in CLT that reinforcement allows us to overcome by the placement of shear in strategic locations, for example, at the CLT interface with a vertical column, as you can see here, leading to these sorts of advantages in our system in a platform framing. I won't belabor this, but if you want to ask questions or seek information from me after, you can see the enhancements here from using high strength fiber to overcome these problems, such as rolling shear. And rolling shear used to apply just for plywood, for example, because of the transverse grain situation in horizontal shear. But as you can see today with CLT, it also is a factor, as you can see in this picture. So this is how platform framing allows us to use high strength fiber and get where we're going to reduce minor axis shear. And here's an example of a minor axis shear reinforcement, as you can see here in the picture. And you take a CLT in this minor axis shear issue, it can either be a piece of RP or bonded a piece of GLB, but the most effective and unobtrusive situation or solution is, of course, to use thin layers of RP that get in and do their strategic jobs at these locations. You can use them also in reinforcements for shear for bridges, where the shear is a max at the end of the span, and you're able to improve its performance either by pre-assembly, as you can see here. This is where bridges are going today in the world, with total pre-assembly with a TL4 truck crash-proof rail system, and as you can see here, the girder unders. And these high-strength fibers are allowing our spans to exceed previous spans. We now work with girder under spans through FEMs, which I'll talk about here in a minute, fixed end moment connections that allow us to move up to 100-meter clear span girder under and carry trucks and traffic on a 4-lane highway bridge. And so that's where this is going with these small components that use these high-strength fibers as a way of improving performance in the end product, the composite. You can see this is an FEM here, shown above there, and this is high-strength fiber being used on the bottom face of a beam in strategic locations. The lower left-hand corner, you see we're placing it in unique positions where the demand produces a stress that exceeds the wood fiber's capability. And this is aramid, a trade name known as Kevlar, for example. And that aramid is placed in a strategic location. It has a coefficient of thermal expansion that a boat matches wood versus steel, which doesn't. I can't have plane sections not remaining plain, so I have to bond it with a material made in a way that accommodates wood shrinkage and expansion also transversely. So this fiber has 0 strength transverse and 5 times the strength of steel on the longitudinal. And that single piece of glue reinforcement we're using here with 0.07 inches thick is equal in tension capacity to the whole timber beam that you see supported here. So then when I get in a strategic location, excuse me, as you can see in this bridge on the bottom right-hand corner with an FEM wood welding joint there at the end, you can get that reinforcement to do the heavy lifting you're looking for to get timber back into vogue in long spans. As you can see here, rolls of reinforcement, 5 times the strength of steel at a fifth the dead weight, strategically manufactured to place in position in these long beams to get us where we're going, as you can see here, with a setup producing the adherence of the RP to it, so that it's bonded integrally to the surface and does not step out of plane sections remaining plain, as you can see here. This also accommodates fixed end moment connections, which are big today, what we call wood welding. This is where we're able to take short pieces, say 11 meters, because you ship it in a container. It's hard to ship break bulk around the world today, but we designed for plants in America, Australia, and Canada, where they basically produce 11-meter sections, put it in containers, and ship it around the world. Well, what can you do? Well, if you want to produce an 80-meter clear span bridge that's carrying truck traffic, you have to have a fixed end moment connection that is slip distortion resistant. So by using an epoxy high strength fiber connection combination, you're able to get to what we call slip resistant or distortion resistant connections that truly represent wood welding. As you can see here, this is pre-manufactured, post-treated, machined before treatment, so that there's no bright wood. And you can see them assembling here using an epoxy and reinforcement, assembling an FEM connection that gets this beam across the gap with small sections turning into big sections through a wood welding program. It's a unique designs that are based on, a lot of structural assessment, that this is where the world's going today with high strength fiber and slip distortion proof connections on a wood weld basis. You can see here the Kevlar being used in underneath this. You see the plastic surrounding the steel. Steel's coefficient of thermal expansion is so great that if I tried to make an FEM slip distortion resistant out of steel bonded to wood within a very short period of time, the wood would have changed dimension. The coefficient of thermal expansion would have been so great, 3 orders of magnitude greater between steel and wood, that steel piece would have debonded from the wood and trouble would occur. And so we isolate the steel by wrapping it in saran wrap so that it can't bond to the wood in any way inadvertently to produce this FEM or fixed end moment connection, as you can see here, with a high strength fiber wood welding the bottom of this beam. So these are projects completed around the world using these different technologies with high strength fibers. You Cartier watch in Switzerland. This is a sawmill in Germany. This is in Austria with a gymnasium. This is a playground equipment material in Switzerland outside of Geneva. This is me doing some quality control checks when I had brown hair, and I did have hair. That was a long time ago with high strength fiber. Now high strength fiber is just a household word in the use of many, many high strength beams that are put out today in the marketplace, as you can see in these pictures. This is Zolig, for example, producing the longest glulam beam made with FEMs for McDonald's in their McDonald's building with low-tar wood in 1999, the big blowdown series of wood where he designed these beams. And this is half a length of beam with 10 smart cars parked in front of it. And we lifted them into place and we made this McDonald's distribution center. We put it together in 7 days, along with Franco's saying, it's all in the planning, it's all in the design. And don't be wringing your hands on the job site, blowing off the time. You want to be spending your time on the front end thinking about it. Dad used to say, spend 90% of your time sharpening the axe and 10% of your time cutting the wood. And that's what you have to do with these mass timber buildings in order to get where you're going. Wastewater treatment plant. This is an open air arena that's longer than a football field in Poland, where the beams are doubly curved and high strength fiber reinforced. You can see many different buildings here. This is in Oregon at Corvallis overlooking the football stadium. This is a swimming pool, all big buildings built with high strength fiber. We're also using high strength fiber today to repair existing bridges, go in and without taking a bridge out, upgrade its capacity, restore it, provide for a solution if it's broken. This is a big aircraft hangar in Idaho where the trusses were in trouble. They didn't meet the code and one of them broke, and they were able to go in with high strength fiber and resolve that and design solutions to put them in place and basically upgrade an existing building with high strength fiber and bring it back into service and extend its life with shear panels, high strength fiber, as you can see placed here on these broken arches, broken beams here, fixed in situ with high strength fiber, shear panels, and so on that allow us to extend the life and the capacity of the piece and upgrade its capacity in place to handle new code requirements, or as in this particular case, where a low-grade piece of wood get into flexural and bending and failed in tension parallel to grain, fix that beam in situ, and doing it with high-strength fiber. So all of the uses today that we see high-strength fiber playing a role, not only in new construction, but in old construction. This is where our wood technology is going today, as we see existing timber piles resolved with pile wraps and injected with slow cure 2-part epoxies to restore in situ and extend life another 25 or 30 years, which gives great value. Or if the pile has burst because of decay, to fix it in situ, as you can see here, and extend life and push it on down the road with wraps that are made in a special way so that the pile, when it expands due to moisture change, due to capillary action, it doesn't lead to expansion stresses that tear that fiber and fail it in tension and hoop stress. A slow cure 2-part epoxy that doesn't overheat and have exothermic runaway that burns up the building, but instead slow cures to restore compression capabilities within the piece itself as a slow, what we call low-cost, cheap modulus bulker. These are the sorts of things, and just to add a slide or two that was picking up on earlier points, decay in wood has often been our Achilles heel. Concrete used it to kill us in the 60s, 70s, and 80s, saying that wood doesn't last. Concrete does. Today, we're seeing the end of that great concrete panacea. And why are we seeing it? Because people that have got bridges, for example, are realizing that concrete doesn't last 100 years, that at 40 and 50 and 60 years, reactive agent issues are all playing a role. Whereas timber, if you do the right job to protect it for downstream, it's going to last time. As you can see here, if we take any one of these environmental conditions away, wood does not decay. Well, we can't take heat away. We can't take the food source, which is wood, of course. We can't take oxygen, but you can deal with moisture. So if your designs are based on keeping the wood dry or treating it such that it won't decay, then you're not going to see a problem with wood. And remedial treatments, for example, like preservative treatments, borate salt diffuser rods, fumigants, are all the ways today out in the marketplace that we can utilize methods to extend the life and provide for durability that matches concrete or exceeds it and get us down the road. As you can see, these diffuser rods with the borate salt that you can install in your piece and extend its life. The borate salt is a salt that neutralizes the acidic content of the pH wave for a decay-causing colony, which creates that acidic environment to break the wood down. The salt neutralizes, it's called a diffuser, and it basically neutralizes the pH wave. You can see them put them in here to extend life. So in conclusion, I appreciate your time. I just want to give you an overview and a sketch of how high-strength fibers are playing a role in today's society with mass timber and causing longer spans, providing for heavier capacities to be carried, and bolting timber back into the arena in situations like bridges, for example, and high-rise buildings. And so with that, appreciate your time, and thanks for putting up with me. I look forward to answering any questions.
Thank you, Dan. Yes, again, lots of information, and we welcome and appreciate the expertise that you've gathered over the years. Yeah, a lot of information in such a short time, says Morel. I see, Damien, you did ask a question about the Cape Town presence of WRD, and I have sort of tagged Paul to perhaps ask if he could just share the information with Damien, unless you want to answer that question. So maybe you could just say whereabouts WRD is in Cape Town.
It's Fishhook, and it's in Cape Town. And if he wants to put a note in the chat, Paul, I'm sure, will respond. I think he's online today watching. He'll provide his phone number and you can get to him.
Super, thank you so much. There's a question from Dennis, Dan, and I think this may be for you. Does the fiber reinforcement contain real plastic, or do they mean it is malleable? So if you could just answer that. Okay, good question. There's three basic fibers today that we're seeing utilized in the marketplace. Of course, Kevlar, which is my preferred one, is an aramid fiber, Polyparatera aramid. It's a very tenacious, get the highest specific tensile capacity in the world of man-made fibers.
That's its density compared to its tension capacity. Then there's carbon, of course, and then of course there's glass. And the workhorses today, for the most part, are aramid and glass. They produce them in a matrix. That's a resin matrix where the fibers are wet out, and that matrix can be a variety of different materials. Traditionally, materials like vinyl ester, for example, or epoxy, polyester. But again, vinyl ester, which is a one-way thermoset glue. Once it's produced, it doesn't resoften and go back into the atmosphere. It's a solid that's what we call a one-way. It's a thermoset glue. And that produces a reinforcement. In that reinforcement, the fibers are pre-tensioned so that there's no initial gap that takes place. Once adhered directly to the timber, they become an integral portion of the timber. Plain sections remain plain, and that fiber acts in combination with the timber element, and it bypasses localized defects. One of the big Achilles heels for timber, because it grows with branches and so on, it creates knots. And the knots are where the branch were, and that creates a slope of grain. And when you get that slope of grain in a bending face, that's what causes the weakness, because you can resolve the bending stresses and tension into parallel to grain and perp to grain. And when you have a divergence of grain, the perp to grain is the weakest strength of wood. And so that's what causes problems and why we keep the big knots out of the bottom face of a beam and bending. Well, if I put a piece of high strength fiber on that bottom face, it transitions the stress around that localized discontinuity and enhances capacity. Typically, a 50 thousandths of an inch thick piece of reinforcement doubles the moment capacity of a piece of wood that is put on, sometimes triples and sometimes 4 times. So those are huge increases to increase the capacity. Well, Dan, you might say, well, yeah, but stiffness is going to take over. But watch for it. In mass timber buildings, fire resistance ratings are critical, and they're based on access and egress, which means loss of section. And if I double the moment capacity, I'm going to significantly increase my fire resistance ratings. And so that's why high strength fiber has really come to play in mass timber in the last probably 5 years. Did that answer your question?
I hope so, Dennis. You can just ping us in the chat if not. Then there was another one. Let's just go from Matt. He says, does heating, ventilation, and air conditioning affect mass timber?
As long as you keep the equilibrium moisture content in the environment down below wood's 24%. So wood is hygroscopic, breathes in and out moisture. It equilibrates with its surroundings. So if a heating and ventilation unit is creating a higher RH, which it normally doesn't, wood, for example, at 21 C and roughly 75% RH will equilibrate at lower than the percent needed to decay, which is 24%. If, in fact, I leave my temperature at 23 to 24, 25 C, and I allow the RH to roll up to 85 to 90, 92%, then that's enough to bring the moisture content in the wood up over 24% because it equilibrates and then decay can proceed. So the reasons we watch HVAC units is that they don't create localized areas of higher RH or higher moisture content, which would lead to localized areas of degradation due to decay.
Yeah, I would say that we had some problems in the past on a couple of buildings because of the cooling system. They were using, I don't know the technical name, they were using cold water below the tiles. So this can create a lot of condensation and a lot of water below the tiles. It is something that in some cases you do not see, but then the water goes down until the CLT or the timber structure below. So it is very important to reduce the humidity and to consider this when they have these kind of things in the building. As I said, we must have a very holistic approach to the design. We cannot work. I'm the structural engineer. That's it. Someone else will take care of other things. We really need to work in a team and to consider all these aspects.
my experience is more residential, so I haven't worked much with AC or HVAC, but I can say for fireplaces that your flues, you have to just keep them a certain distance away from the timber because of that risk. And if you have a heat source, you might just have more movement or drying cracks in your timber, but that's just a visual thing. So, timber moves a lot, but as long as you let it move.
How do CLT buildings perform in terms of earthquakes as compared to RC reinforced concrete?
One of the great things about timber is its ability to absorb acceleration forces. When you build a concrete structure, it takes a lot of special design to handle acceleration forces. And earthquakes move the ground very quickly and accelerate the base with respect to the upper portions of the structure. And so timber, because of its low E, and lots of times low E, modulus elasticity, which relates to stiffness and deflection, it's low E, it's given its Achilles heel. But quite frankly, in earthquakes, wood's Achilles heel, which is its low E, turns into its huge benefit because what it does is acts more with elasticity to earthquake acceleration loads. And quite frankly, timber is an excellent material to use in an earthquake-prone area. I love to do it. When I get a design, Vancouver, for example, Japan, I designed a bridge one time in the northern island of Hokkaido in Japan, where they were really worried about earthquakes. And it was a pleasure to be able to design that bridge in timber versus reinforced concrete. Wood is just superior in its performance there.
Yeah, I would add a couple of things on top of what Dan already said. One thing is the lightness. Timber is about 80% lighter than concrete.
Yes.
So it is. It is 500 kilos. It is not 8%. Sorry, it is 500 kilos versus 2,500. So it is very light, and this helps a lot. And then another thing is that timber performs very good when the loads are very short. So the earthquake, the duration of an earthquake is a few seconds, luckily. So timber performs very good when these loads are very quick, like from seconds to a few minutes. The combination of that, the result is a very good material to use in case of earthquake.
I just wanted to add that with earthquakes, then timber is great because of all the things that Franco and Dan have said. One might just look at the connections as well and ensure ductility in your connections. So much of timber design comes down to the connections. It's the same for seismic. So the timber is great, but if your connections are too stiff and take too much load, then they can break. So just something to consider in seismic design.
Thanks, Michael. Super. So thank you to all of the speakers. Really, really insightful presentations. You have got lots of compliments in the chat. So without further ado, I want to just hand over to Tafadzwa Nyanzuda. She is from the Department of Trade, Industry and Competition, and she will just give some brief closing remarks. So thank you, Tafadzwa.
Okay. Thank you, Sam. Thank you to all our presenters, and hello to Franco. You've been with us in this journey. So thank you once again for another presentation. I'm sure this is your second presentation in the series of webinars that we have been doing on Talking Timber webinar. Thank you to Dr. Dan for such an insightful, very insightful presentation. We have shared quite a number of links already in the presentations, so I am not going to repeat to that. Sam, if you can just share on the furniture design competition that the Department of Trade, Industry and Competition is running, and it will be closing on the 30th of September. So we noticed that we have quite a number of architects, and they always participate in this furniture design competition. If you could enter the competition, and this year we've aligned the theme of the competition with last year timber design competition. So last year we designed 3 floors on top of the Fibre building at University of Pretoria. The theme for this year is to design furniture that is going to go into that building. So we look forward to your designs, and the competition closes on the 30th of September. Register for the timber construction conference that is upcoming. The link has already been shared, and also you can watch the previous webinars that have happened. You can also go to the timber to the Wood app and do some courses that are there on the Wood app. And it's overwhelming, the participants, architects that have joined these webinars, and also the engineers that have also joined the webinars. So we're really grateful to the built environment to be participating in these webinars. I had asked a question to say, what has been the role of the policy in timber construction, but I guess it will be a topic for another webinar that we will have experts telling us how policy has also facilitated growth in timber construction. So to you all, thank you very much for joining the webinar, and I'll take it back to you, Sam. Thank you.
Thank you to Fatwa. Yeah, again, lots of compliments. And to Damien, thank you very much. One of the best webinars to date, which is always good to know. We aim to please. And as always, we welcome any feedback. You have our emails, so please do reach out to us if you do have any comments, suggestions. We always welcome input. There's always so much to learn. And as we've mentioned before, there are some past webinar videos on the Sawmilling South Africa YouTube channel. I posted the link into the chat. Thank you very much, and wherever you are in South Africa or even the world, Canada included, we just wish you a lovely day and take care. Thank you so much.